Hello. Okay. All right. We're how many people are online right now? We're recording, and we have 11 participants. So meaning that half the class is up right now. Even my boys are staying at home. They have 4 days. They would have 4 days at school after a long weekend and before spring break. So we said, yeah, COVID cases going up. Yeah, they're staying at home. So in case you're wondering why half the people are gone, I'm assuming that's the case for everybody this term this year. Um, Part of the reason because I also know you guys are everyone's sort of stressed out at the end of term. I know I am. I have to design a bunch of exams, for example, today. I also have to pass in. I've done all your grading of all your sprints. I just need to pass in the project 6 sprint information. Uh, and then on Thursday we have the usability test. So everyone, I need to make sure I clear up or make sure my instructions are clear for how to post that information on CU Learn. It would just be everyone, you're going to see other people's posts for what their project is and the instructions on how to test you post the instructions on how you want people to test your project. This is not, do you like it? It's, can you do the thing that's critical? Say, if you say you're going to compare energy usage across between detached houses and high-rise apartment buildings, can you do that with your system? If you're saying that you need to see how long your commute time is at the beginning of the day, can the person actually do that? Can they actually make that estimate? You can give them a specific task, which is the fastest path, or what's your commute time from here to here today. You want to be specific enough that you can actually make sure that they didn't get confused by, I don't know where that is in the city, compared to, if you give them this task, can they accomplish that task? If that's what the task that you would expect them to do, can they do it? That's what we're looking for. That's for the usability test. What you're looking, again, let me reiterate, we're looking for things that go wrong. You're not trying to play it safe. You're trying to play it, you're trying to get feedback so that you can improve your system. And so you don't want to go crazy on that approach. Don't say, like, here it is, I'm not going to give you any instructions, go, right? You don't want to do that, but you do want to be open-ended enough that you're actually legitimately testing what you would expect people to be testing. If your system is for finding places to exercise outside in Ottawa, give them that as the task. Don't just say how many skating rinks are around you, or you can even say how many skating rinks are around you, but you want to be as close to the real task that you are trying to get them to accomplish as you can, so that you get legitimate feedback, so you can legitimately, time permitting, legitimately fix your system. That's what we're aiming for. You're expecting to get problems. You're expecting to find errors. You're expecting to find things to improve upon, because nothing is ever right the first time. So I know I keep on going back to the same well for information, but Apple products are very, very good at this particular thing. Apple, despite everyone, sort of cult of Apple saying, oh yeah, they do everything perfect. No, they don't. The original iPad had no camera, could not multitask, could not multi-thread at all. And they said, you don't need that. That's their secret, is always saying, oh, you don't need this. And then in version 2, they go, and magically we have that thing you needed the first time, right? They said, no way we're going to put a camera on this. That's stupid. Why would you put a camera on an iPad? And then what happened to the iPad 2? Oh, conveniently, there's cameras on it, right? They figure out what they're missing. The same with the Apple Watch, same thing. Pretty much every single software, every piece of software, every device, they figure out what people want only after the fact. Sometimes the people don't necessarily know what they want, but you'll find out soon enough. The observant person will actually be able to tease out that detail. Okay, so what are we doing today? That's the real question. So we were looking at scientific visualization. Now, this is the, in theory and practice are the same. In practice, they're different, that sort of thing. In theory, scientific visualizations and information visualizations should be the same thing. It's visualizations, right? But because scientific visualizations, sort of how that we define it, because there's already a spatial component to them, and you can't just throw it out or anything like that, because there's this inherent spatial component, it means you have to do things a little bit different. It also means computational ability is the challenge. That's the bottleneck. It's not actually human understanding, it's not usability necessarily, although there is that now. But a long time ago, it was computational ability. You could not crunch the numbers well enough. We'll actually see an example, I think a couple examples of this, where, yeah, the there's a cadaver, I can't remember the slice drop, but there's I forgot to look at the name of the project. But there are lots and lots of visualizations out there that would be ridiculously computationally expensive. I rewatched one of the videos actually, where they got this, they do this proper scan of a full cadaver, so dead body, and you can examine the scan, and you'd say, "Oh, of course you can do that." It was scanned in the 1990s. There was no way in heck they were doing that in real time at the time, like when you're trying to manipulate and navigate through uh, the anatomy of an object or of a person in this case. And as a result, that bottleneck, that computational bottleneck, ends up being part of this field. It's inherently built in that you're dealing with data that is way bigger than you would expect. That's the scale is the issue. Because with a line graph, um, the red light groups, though, so the best group, whatever your name doesn't match your actual project. So um, I told you seeing red at the beginning. The best group, the group that's looking at red light cameras in the city of Ottawa is hitting this. It's not even necessarily, it is spatial because you have places in Ottawa, but it's on a map. That's fine. So we have map information, but those places in Ottawa, the amount of data that they have at any given time is somewhat overwhelming. And so if you put a line graph for each traffic light in Ottawa, what do you get? You get spaghetti. You just get this big pile of lines, and you can't read it. You can't deal with it at all. Scale ends up being the issue. The scale is the enemy. It's actually why when everyone was like, "Oh, it's a bar chart," or "I'm going to use a pie chart," I keep on going. That's not really a visualization because it's so simple. It's like saying, three-letter words are the English language. No, it's really the simple form of it. It's the minimal amount compared to an actual novel, let's say. Uh, Scientific visualizations have this issue. Now, they also can be broken into three different parts of three main ways we look at data. One of them is we just have the geometry. Great. We can actually, you have geographic information. We can put the derived information right on top of it. So we can put glyphs and stuff like that on top of it. We have spatial fields. Spatial fields we're going to look at those. So ISO contours, volume rendering. It is the actual outline, what the layers actually look like, the actual things that you're seeing. And then we have vector, tensor fields, scalar fields. We're layering some kind of glyph on top of our image, or we're putting lines on it, oftentimes invisible lines. So particle fields would be another one of these things where we can show the particles. The particles are not actually visible. They're not actually there. If they are there, then we're talking about other volume rendering, or we can, uh, yeah, particle fields, I think fits like a geometric particle field would fit into this vector tensor field thing. They're individual dots, but you can sort of see how everything's flowing. Not my area, by the way. So if I trip over a word, please bear with me, but I understand enough of it for sure. So what we're looking at today, we're going to look at some spatial fields. We're going to look at tensor, vector, and scalar fields, how we can represent that data. And then we also look at geometric projections. And time permitting, I want to actually look at dimensional scaling, which plays really well into this. Although dimensional scaling is ideally for information visualization, these non-spatial visualizations. What's really strange about that field is sometimes we have so much data that's abstract data that you try and represent it to 2D space. It's a really, really difficult open question. And it's completely open. We don't know what the answer is. Uh, if you like math, which we're not going to hit the math today, but if you really like math, that's your field. That's a great place to go. It is extremely math heavy. It also maps directly with machine learning and data mining. They all sort of play together, these three different fields: dimensionality reduction, data mining, and machine learning. They're all sort of three parts looking at the same kind of problem. So what's so special? We have lots of data. I'm just going to blow through. These are slides we already went through. We have a lot of data, constrained ways to look at it. We have the structures can be somewhat present or semi-present. So sometimes we have structures in there, and we have occlusion and shading issues that come up. And when we looked at spatial fields, we talked about scalar fields, tensor fields, uh, the idea that I can have just throw a whole bunch of glyphs on the vectors on my diagram on top of my diagram, and I can get a feel for where the directionality of things is going. Scalar field is just what's the magnitude or what's the value at each one of these cells. So if I'm looking at an airplane wing, every single part on the surface of the wing, what is the wind flow at that point? Vector fields have a magnitude and direction, and then we had one step further than that, which is the tensor field, which is like vector it has a magnitude, it has a direction, and it has a whole bunch of other data as well. And they get really, really crazy, crazy, crazy. We won't be grilling you on this one, but they're really useful if you need to pack in a lot of data all at once. And this is not for casual use ever. This is for domain experts that have been staring at this thing and train their eye for seeing this. Much like you train your eye to see a lot of other things. If you're an artist, you train your eye to interpret and see other people's art. If you're a chess player, you train your eye to see patterns on the board. You don't actually see the individual pieces. You see them, but you see the board in a very different way than an amateur does. So same thing here. So, and we can look at how you can compare tensor fields. That's what we looked at. We also looked at, when you're talking about vector fields, which one's the most effective. And we said this is actually not a little bit surprising. This is actually was the most effective for reading off spatial information, although these are good for different spatial tasks. The encoding, how we do the vector field, changes how we use or read off the data, which by now should not be surprising to you, but it is something that they can empirically validate. We even looked at the fact that Leonardo da Vinci, way back in the day, looked at fluid visualization. So this is a fluid flow visualization. It is looking at how fluids, air, water, the big two, right? How they flow around an object and what you can do with that. And so instead of just having a whole bunch of little vector lines, a fluid flow visualization can contour around it. You can do both, but there are a variety of different ways of looking at how things travel. So one of the things I don't have a lot of on the slides are you can actually use animation. That's one of our options. We have animation. We have our vector fields or tensor fields, depending on how you want to look at it. We actually have flow lines, fluid flow lines that go around it, like this thing right here, which, by the way, we can encode. We can color a fluid flow line with different colors. We can color code a vector field with different colors. We have a mark, which is its arrow, and then we have a whole bunch of channels we can add to it. We can use the width or the length of the line or the arrow to indicate, just say, a different dimension. It starts becoming starts becoming a tensor field. We can encode each of those arrows with multiple channels of information. It's still a vector field, but we can try and pack in more information. And in case you're wondering where this comes up, it comes up everywhere. So this is the sheer joy of, I was looking for an example for 2021 or 2020, I think is the last one. I wouldn't have done the new one this year. For the same conference in 2020, but they were all actual camera, high-speed camera. Well, didn't find a lot of simulations. I found a lot of actual high-speed camera visuals of, let's say, people a lot of times for COVID breathing and how the air leaves your mouth. So when you're singing, what's the airflow versus when you're talking versus when you're just breathing in and out, what the airflow looks like. Not really a visualization, it's actually showing the particles based on an infrared camera. But if we're looking at, but it relates very much the same way. We can look at how particles flow, and we can look at how paint dries, for example, it's simulating paint drying, or we can simulating air jet, sweeping jet for fluid oscillation and cross flow over an airplane wing, or this one is starfish larvae and how they eat, eat things, so what what their prey is, I guess, and how they swim. Back to the more practical side of things, remember that whole heart? I keep on bringing up this heart research because it keeps on coming up. Uh, Again, Michelle Borkin's work on cardiovascular health. One of the things she was doing as well, not just crapping all over rainbow color maps and mapping it to non-spatial dimensions, and then using a more muted color scheme, changing the color scheme so that the cardiovascular disease pops up more. Not only was she removing the spatial component because that didn't matter, but she also looked into using fluid flows for cardiovascular health. So here would be a fluid flow using lines, fluid flow lines in the top part here, coloring it based off cardiovascular health. Here, she's using a vector flow on the bottom part, a vector flow with the sheer number of glyphs, these vector glyphs, indicating the density or the amount of, presumably, amount of pressure, and where the blood is actually flowing throughout the system. And you could have tried it, maybe you could have encoded the arrows in a different way, or you do a number of other things. But this is the kind of things that people look at when it comes to cardiovascular health. Sort of, I'm at that age right now that I actually want to look at this, or I want to have other people look at this and know that things are going correctly. Um, Actually, I had my heart checked a little while ago. They weren't using this. They were using other tactics, other techniques. And I was like, that's my research field. Oh my God, it's using it. They're using it to, protect my health. That's fantastic. Right. So they would do an echo, they were doing ultrasound around your heart and measuring the openings, measuring the flow. They actually could detect using the Doppler effect. They're actually determining the directionality of blood flow in your heart and the amount of blood flowing. And they were actually using color. They're using a rainbow color scale to indicate, and it's a rainbow color scale, but since it's 3D, they're using a rainbow color scale to indicate the directionality of the blood. So they use red for one direction, blue for the other. Different hues to indicate different categories of the blood flow, right? They're using the different colors to show the directionality of the blood. They're using the intensity of the color, where I think the saturation of the transparency of the color to indicate how much blood was flowing and which direction it was flowing in. And they were actually able to take little measurements. They were able to overlay geometric primitives on top of it to see the heart health. In case you're wondering, my heart seems to be perfectly fine. They thought to look normal. But this is the kind of thing that they actually do. It's this field applied to your everyday life. They were actually using it for my eyes. I told you, I think earlier in the term, I got really bad eyes. I got really weird blind spots in my eyes. Turns out that's what they actually do as well. They'll have a scan of the back of my optic nerve, and they'll be able to outline and indicate places where they think there might be problems in the eye. And they're using color to indicate, spatially laying out color for problematic areas. They're using a spatial field. So, but that was for fluid flow visualizations. In case you wanted to see other cases, here's animation being used to indicate this. We can color it based off of the category of data it is, which way the pressure is going. Is it positive or negative for the Reynolds number 100? That's not Ryan Reynolds, in case you're wondering. There's a different Reynolds. Right? And you can actually see the velocity, which way the velocity and which directionality the velocity of the fluid is going at any given time. It turns out, so here's a little secret that I tell everyone about, and it's one of those weird things that I've learned to be very afraid of the world. So I used to work at CD Adapco. I've talked about it before. I'm going to show you some CD Adapco stuff in a second. I was talking at various times to the world expert in name a field, essentially. So one of them is a world expert in turbulence analysis. Young guy, but that's what his specialty is, turbulence. Turns out when you talk to this guy, he's like, yeah, we don't know anything about turbulence. So we have all these planes flying in the air. We know all about turbulence in this general sense. We have no idea the nitty-gritty details of how it actually works. Still open. What you're seeing here is still open. There's still research to be done. Scientists are still trying to figure out how all of this stuff works, and that's why they need these visualizations. It also turns out another one of my coworkers is an expert in jet engine turbines, and it turns out jet engine turbines are, how do I want to say this? The operating temperature of a jet engine turbine, the things that that power your airplanes, the operating temperature of it is hotter than the melting point of the steel. You heard that correctly. The melting point of the steel is a lower temperature than the optimal operating temperature of the turbine. So their solution is they have these little tiny holes throughout to make a jacket of air around the steel to keep it from melting and blowing out the back of the airplane. They get so good at this sort of thing that they say, well, we have 4 of these. We don't need 4 of these. Let's go to 2 of these. Every once in a while, you'll see a video online where one of these things gives out. Instead of needing 4, they say, hey, we just need 2. The thing is ready to melt and blow out the back of the plane at any given time. Yet they go, yeah, we're pretty sure it's going to be fine. And yet, the thing they're terrified of, the thing everyone should be terrified of, is that the software in the plane is more error prone and more dangerous than this turbine, which is operating at a higher temperature than the melting point of the steel. That's not the scary part of the plane. The scary part of the plane is the software that's being designed. I tell this to my students when they do computational like proof of correctness for programs. And it's like, yeah, the rest of the world is building planes, they're building bridges, they're confident in how it works. The software being built, the visualizations being built, everything that we do software-wise is the more error-prone out of all of those things. That's why we have to learn how to program correctly the first time. So here I don't have great visualizations for this. So let me walk you through them. I found a couple of videos. I have way too many videos today, but let me walk you through a couple of them. First of all, this is from, I think, when I was at CD Adapco. It turns out they talk about like, oh, let's look at how, fluid flows around a propeller for a big boat so that we can do more efficient transportation. Oh, let's look at how batteries discharge. It turns out one of the big customers that they don't really advertise a lot of, the US government uses our old software or uses our software a whole lot. I wasn't allowed to talk to end customers as a result because I'm a Canadian citizen working in the US company and I do not have top secret military clearance. Yeah, it's that sort of thing. Because that's what they use this. One of the things that they use it for is if you want to make an airplane, you don't build the airplane. You build the simulation. You build a simulation for it. You build your mesh. You build your model, your computational model. Before you make it anything out of metal, you figure out if it's going to work or not. And so you run a computational simulation, which is a whole lot cheaper, orders of magnitude cheaper than building a plane, putting it in an actual wind tunnel and seeing how the plane operates, or train or missile or whatever you're testing. So this is them testing how an airplane would travel through the air. Notice what we have. We have scalar field, so we actually are encoding where the high wind speed is hitting the plane at certain areas. We also have a fluid flow out the back indicating the invisible components. When it's on the actual hard mesh, you can actually encode the mesh with a color, so giving you a contour. But if you want to see how the wind is going, you can use a fluid flow at the back. Two different techniques all at once. Here we have a vector field with a I always want to say shouldn't be an isocontour though. It's a scalar field, color coded spatial scalar field on top, uh, for a three-dimensional space. Here we actually have 2D slices. They have planar slices of the system at various positions that you can manipulate and look at. That's what you do with a brain scan. A different technique. Again, you're color encoding based off of what you're trying to look at. You're also looking at the turbulence. You have a fluid flow simulation. You have a fluid lines indicating how the data is looking. People get very, very good at this, but it all breaks down to essentially three different things. We can color the object, we can give you a line or a bunch of vectors and that sort of thing, or we can give you slices of data. I can give you the 3D model itself, and that's coloring the 3D model as well. So we're going to look at some of those other parts. So spatial fields. We briefly talked about this, but here would be, I have a bunch of spatial fields and I can color them, right? So if this is one, if it gets a bit darker, 3, the numbers are not matching between the two. But this would be presumably a very intense area. This is a not intense area right here. And you've seen this. So let's actually, so here's the idea that we can also do. So we have scalar fields. We can just color each individual cell block based off of what we're seeing. That's one. That's a scalar field. We have a vector field, we have a tensor field. So, by the way, this would be scalar field right here. The other option we can do is we can try and find all the common chunks, all the common parts, the same intensity, mark those off, and just say that's one color. Okay, go to the other part, another color, and just sort of discretize the space. So find the contours where they're all sort of the same and say that that's one area. This is an isocontour. This is a contour line that shows a single value that encapsulates everything we're looking for. So although it's not perfect, this might be this part right here, sort of presumably like indicating this part. If you can draw lines around common areas over and over again, you can get the contour or the approximate shape of an object without getting overwhelmed with all the minutiae, the nitty-gritty details. That line itself, though, tells you a whole lot. So instead of coloring in the cells, all I need to do is draw the outline around this thing, around this shape, and color everything the same and just draw the outline around this, the outline around here, let's say, the outline around here. I can just draw the outlines versus filling in the inside. That's an isocontour. And you're probably wondering, why the hell would you do that? Oh, because you already have seen that before. Oh, is that? There we go. You've seen it before. Anyone that's ever used a map, especially gone hiking using a map, has seen an isocontour before. Caddy Hill, notice the hill is all the same color. I didn't do, so I've used color to indicate like at the bottom of the basin, and here is the actual hill itself. Right, we're looking at, here is a river. I have color indicating one thing, like categories of information. It's in the valley, it's on the hill, it's wet, you're in the river. Right? And oh, I also have roads as well, right? I have different encodings using color. Since I have already using color, I need something else I can use. That's where the isocontour comes in. So if you look at this, take a quick look at this and tell me where the steepest parts of each of the hills are. That's where isocontours are useful. So on this part of the hill here, where's the steepest part? Actually, how would you find the steepest part? Maybe someone can answer me because I think half people are asleep maybe now. Where's the steepest part? If I look at a hill like this, how would I know where the steepest parts are? Yeah, lines close together. Thank you, Kara. All right. My next door neighbor was Kara. You're a Kara. I got to update my pronunciation. Same spelling, by the way. But she's American, so it's different. The lines that are close together tell you when it's really steep because that's all the lines everything within that one line is one height, vertical height. And then the next line up is another vertical height. And so if they're really packed together, you know that it's a very steep hill. You can read off critical pieces of information just with isocontours. That's why we use them. They're very, very powerful in terms of conveying information, but I didn't have to overload the user with a whole bunch of different colors. If I rainbow colored each of those areas, it would look like you're hallucinating. It's not remotely subtle at all. The isocontours give you that little gradient for free with relatively easy to be able to read off. We also have isosurfaces. Everything that is in the same on the same surface, colored the same way. We do another surface, color it the same way. Or we just show that one surface and we hide everything underneath it. That's one of the big ways of doing it. So the scalar field is what you got, one value per cell. This thing is every single thing that is the same value, color it the same way, show it, remove everything else. So layers, think of it like layers. Isosurfaces are, I want to show this layer, I want to show this layer, I want to show this layer. Here's the other approach, volume rendering. So if I want to actually show the geometry itself, not colors on top of the geometry, but I want to indicate something about the geometry itself, these are some of our other techniques. I have an isosurface, I have a volume rendering. They're very different. This is the one that's computationally expensive. This is every single value in the entire, system. Astronomy uses this a lot. Every single thing that you're showing, you show, but you put it with a transparency. So every blood vessel is shown, every piece of cartilage is shown, every single ligament is shown with a transparency. So that little bit of opacity and that transparency allows you to actually get a sense all of the skin is all in one group, and because it's all stacked on top of each other with the same color, you get the look of skin. Versus over here, you see through the first layer of skin, then you see some blood vessels, and you'll see red as a result. A little bit of distortion from the skin on the front, but essentially by showing only a very little amount of each layer all the way up to where you're viewing, by making everything transparent all the way through, you get a sense of where everything is all in one go. So this is show me a layer. This is show me everything just a little bit. Make everything semi-transparent and see if you can see the whole view. You can also do slices as well, but that's a different problem. Okay, so this essentially is by making it transparent, the colors bleed through one to the other, and I get this transfer function. It transfers all of this information to the screen, and I can get a sense of the entire output. This is what I was talking about, but I figured you didn't need to see an old cadaver. It's probably very disturbing for many of you. So we're just that's one screenshot. Hopefully that's not too disturbing. So the Visible Human Project, have a look at it if you want to have, if it's fascinating, I find. Let me walk you through what they're doing. So in case anyone doesn't want to watch the video. The idea was this person donated their body to science when they died. It's a cadaver of a 47-year-old man or something like that. And they did a full scan of his body. And then afterwards, this is what the grotesque part is. They froze him all the way through liquid nitrogen and then did minuscule slices, less than a millimeter thick slices of his body from his toes all the way to his head. Just sliced him one little bit at a time, scanning what he looked like at those various slices. Honest to God, they sliced him up into little tiny, like minuscule paper thin amounts, which is pretty grotesque. But this is being done in the 1990s, by the way. So really well ahead of its time. As a result, they have every single slice of this person's body all the way up to the top of his head. It's completely open source. It's completely open for you to look at. You can play around with this thing. You can take, and because you have the entire scan, you can do the projection this way, this way, this way, this way, any angle you want. You could take a virtual slice of this person's body and see things. What's even further is as soon as you start getting better machine learning algorithms, you start getting better uh, algorithms in general, you can start detecting organs, you can start detecting parts of the body. You have all the data points for the entire body, and you can detect the blood, the circulatory system throughout his body. You can detect the how his renal glands are working. You can detect how his hair follicles are working, or name something like how there's an example of his knee, and you can pull off individual layers of, I would just want to see the bones for his knee. Okay, now overlay the muscles. Now overlay the ligaments. Now overlay the circulatory system. You can remove individual layers, like an isocontour. An isosurface allows you, I only want to see the bone on the outside layer of the bone. Great, we'll show that. Or I only want to see the circulatory system. Great, we'll show that. We can look at individual parts and piece them together. Or we can do what we're doing right here. No, that's actually a slice. That's a planar slice of the body. Or we can do a semi-transparency all the way through, which gives you a sense of where everything is, how things are sort of built together. That would be that's the volume rendering. So I can look at the knee that way. We have a whole bunch of different techniques here. Speaking of which, what I'm going to ask you to do is, I would like you to take a quick screenshot of this after you play around with it. But I'd like to take about 10 minutes because I can talk on blue in the face. But playing around with this sort of starts making sense of where everything is, how things work. Slice drop, it allows you to look at, in this case, a healthy brain of a 14-year-old male. The person didn't die or anything like that. It's a healthy brain. He just got a proper CT scan of his entire head. And you can look at blood flow. You can look at nerve fibers going throughout the brain, how long the nerve fibers are, which is very similar to a fluid flow, fluid lines. We can look at semi-transparency. You can look at isosurfaces. You can look at all of these different parts, everything that we've talked about, including how it rotates and how you can get completely lost in this thing, which is part of what we're looking at. So let's take about 5-10 minutes, say 10 minutes. We're going to look at slice drop and see, hopefully, checked that out a couple days ago just to make sure. Play around with it, see what you can come up with, take a screenshot of it. So just take a screenshot, put your name on the screenshot, pass it into lecture 18, which is the SciVis lecture on the drive, and see where we go from there. But you can explore different views. There's hidden toolbars along the left side of the image you can look at. You can look at 2D and 3D, but notice 2D is just a slice of a three-dimensional space. And we can look at volume rendering. So we can look at the brightness contrast, so window level on the right-hand side, the data thresholds, how long a nerve fiber should be, what the threshold is. And you can change those color schemes. You can just play around with the thing. It gives you a sense of what people have to deal with when it comes to scientific visualizations. So with that, I'm going to pause things for a second. I want you to look at slicedrop.com, take a screenshot or a screen capture of whatever the heck you come up with, and pass that into the Google Drive. Let's see if I can get slice drop myself. There we go. New example. Oh, that's just a slice. What kind of mesh are we doing? Fibers. And here, faster. Okay. I don't know why my thing is not showing up the full brain. It should be the full brain in here. Resize. This one. Oh, there we go. This one. This is the one I was playing with. And you can check out if it's 2D or 3D. You can check out different things, various capacities. And play around with it. Yeah, so I was playing around for a little while, so you guys can probably actually, uh, whatever you found, take a screenshot, post it. Let's see what you come up with. All right, nice. So far, so good. Everyone else, you can post what you have. I'm just going to blow through a couple of these. Oh, nice. So, by the way, who actually liked, just I'll leave it open as a question, but uh, who liked the 2D versus the 3D? Notice that there's a combination of the two. You have a two-dimensional plane with the fibers popping off of the two-dimensional plane. Nice. And notice I have three different planar regions that are giving me cross sections. That's what you're seeing on the other side. Cross section, and you're getting the orientation for where it is in the brain. So we have just the fibers, mostly predominantly transparent. Notice what the planar regions are there, but you don't see it in 3D afterwards. Oh, your region of the brainstem. Oh, that's what I should have been looking at. Brainstem. Brainstems are awesome. Um, so the brainstem back here, right? Very, very critical parts. You don't get that sort of orientation of where you are quite as much as the full human brain, but it still works quite nicely. Nice 2D, 3D. The purple is a little distracting, but that's perfectly normal. And you can play around with it. That's the point. And if you want to remove all the other context around where everything is, but notice with the fibers, I see where the planar regions are, but I don't have any uh, context around where those fibers are in the brain. I just see the fibers. I don't necessarily know where the brain is oriented because I don't have the 2D or 3D in the brain. And do we cycle around? I don't think we cycle around, but very, very similar to what we had with the planar sections and the fibers relative to that. Oh, cool. Nice. Barely any transparency, just get enough to give context and where the fibers are relative to that brain. Wow. Yes, you're coming up with things I've never seen before. So cool. I don't know if I've cycled, but that's also awesome. Oh no, that's not cycled. Very cool. Right. But notice the amount of luminance, if you don't have enough luminance, it's going to be hard to look at. It's very difficult to get the right view, and every person's going to be different. There's a lot of playing around with this space. That's part of the problem. Also, if you're trying to get a sense of what the person's amygdala looks like, or someone's cerebellum looks like, you have to do a whole bunch of scans. You have to go through a whole bunch of scans and see the planar sections and try to make sense of what the area looks like. Notice how you actually interact with the system. How are you playing around with it? I mean, you're somewhat guessing right now yourself. I'm assuming you're not neurosurgeons, but most of us are playing around with how these sections are working, how the planes are working, how we can modify certain variables. But notice if I'm trying to make sense of what these fibers are, where they are located, how they fit in the grand scheme of things, how I can look at a particular subsection of the brain, there are certain techniques I want to use. And you'll also notice, and maybe you didn't notice it, but I think you probably did, how damn slow this is. Now, this is going online. Fine, that's going to be slow. But this is not exactly super high resolution either. This is not, um, presumably not a modern MRI doing the scans here. Therefore, notice the amount of pixels that they're kind of pumped through this system. If you have all of those, the entire brain, every last little bit, the high fidelity scan of the brain, and you're trying to do each one of those cells being semi-transparent and they're going all the way through, it's very computationally expensive. It's very hard to scale. That's why scientific visualize this is very much in the realm of graphics. How do you deal with ridiculously complex systems and how to deal with um, virtual cameras and how we just uh, View planes, virtual cameras, and how we actually project or render a full system like this. It's the realm of computer graphics right now. Oh, wow. Oh, that's interesting. So why does that weird distortion bump at the front of the brain? Oh, it's a projection of the other plane like this. Okay. Part of the brain. Okay. Oh, these are so cool. Nice. Notice if I have red and pink, orange and pink, you you get a sense of where you are in the brain, but you don't really actually see any parts of the brain scan, right? So it's actually very difficult to pick out individual components on the brain. They actually do those components actually are important to figure out where the cells are. So this doesn't give you the orientation where it is in the brain, but you can actually see various hemispheres of the brain, where the cerebellum is, for example. You can see, so this would be the occipital lobe back here. This is where we have sense of sight. And if we wanted to see where that connects to the temporal lobe or where it connects to uh, premotor cortex or something like that, that's what we would be looking at. Oh, that's really cool semi-transparency color. Although really hard to see from the planar slices. Is that the last one that we had? I don't know. I thought those were really cool. Very nice work, guys. Uh, so, I mean, while we're doing this, all right, let's get back into what we were looking at then. So, I'm hoping this gives you some sense of like the crazy complexity. Even if we don't have fluid flows, we have those fibers. It's going to be very similar to what we were looking at with the fibers, what a fluid flow line looks like. We didn't even have vectors on this thing. There's a slew of sorry. There is a slew of different techniques that we have for how we render and how we deal with scientific visualizations. There's only a certain number of ways we can do it. We can color the actual items that we're looking at. We can overlay a color on top of it, which is a scalar field. We can just throw lines on this thing or glyphs on top of this thing, or we can do two-dimensional slices. So here's what, here's what if we're going to go back to isocontours for isosurfaces versus volume rendering, here's what a volume rendering looks like for the human skeleton, for your brain. Here's what an isosurface looks like for the inside around vital organs. Notice the pros and cons of each, though. This thing tells you exactly what the individual components are, but it doesn't give you that sense of what's inside. I have, let's say, a heart here, or let's go with a kidney here. I have a kidney here. I don't know what's inside that kidney because the outside surface is occluding the stuff inside. I have to make a choice. Do I show the outside, which is important to give you the shape of the object I'm looking for? Or do I want to see all the gooey details inside? I can try and do both, but I have to be able to isolate just the kidney here and then do the volume rendering of the kidney. Because the volume rendering tells me if I have a tumor inside the kidney, let's say, you would see it in the volume rendering. If you see the isocontour, you're not going to see that at all. If you do planar slices, you might miss it because you're only seeing one planar slice of the entire space, not the entire thing. There's all of them have pros and cons. So here, if I want to see individual components, isosurface. If I want to get a sense of the entire patient all at once in that area, volume rendering. Distinct object, distinct thresholds. They give you surfaces. The blending and transparency gives you some information that you wouldn't have otherwise. Like you have some kind of injury in your spinal cord right around here. You'll detect that. Some kind of weird bleeding in your spinal bleeding of the spinal fluid within your spine, you'll sense it when you do a scan with a volume rendering. And then when you get that, you find where that thing is, and then you can sort of track it down, that little individual part, and then you have an isosurface view. Here's another example, right? This is me doing, so turbulence simulations. This is turbulence going over, I think the water is going over each of these tubes. I forget what this example is. But if I do an isosurface, I get these sort of spaghetti-like looking shapes. And you think they're distinct, which they are not. They're fluids. Right? But sometimes I want that. Sometimes I want to see how all these fluids work together. Sometimes I just want the general impression of how things look. Smoke would look like this. And so a volume rendering, it looks like a lot like smoke, right? You see through it, but because more dense areas look darker, you can actually get a sense of how everything flows. Here's, I do believe this is B5 star forming region. So here is the star forming region. Here's a bunch of stars being formed in the region, in this area of the galaxy. Here it is as a volume rendering. The volume rendering gives you that sense. This looks like a terrain map, right? You're fighting your visual processing system to see this, but you can see more structure with an isosurface. You get the sense with the volume rendering. And in fact, they've actually already done most of this stuff. So open space, you can have a look at this. See if I have the video of this thing. Not very long, so.
We present work on visualizing planetary surface data for science communication. Our application reads datasets from a vast number of sources, contextualizing them in space and time. Dynamic processes can be visualized interactively. Using navigational data from space missions, we can visualize the process of the data acquisition itself. The work is implemented in the open source astronomical visualization software, OpenSpace.
Right. I just think that's the coolest thing. So I'm nerding out on that. True. But OpenSpace it's doing planetary visualization. So they actually mapped out the moon. You can actually walk around the moon, essentially. It's an isosurface. Now, if you wanted volume rendering, it's a different beast. Yeah, but you're looking at a galaxy, you might want to do a volume rendering for that. They have different purposes for it. And OpenSpace presumably does both. Here would be an isosurface for, I think this is, I'm not even going to show this one, but I think this is earthquakes in California over time, and you're actually seeing the shock waves coming from this. But notice, because you can actually show semi-transparency, you're getting the overview of what the land looks like, how it's impacted things, and what the impact of their earthquake is. And this I find a little weird, so I'm not sure if I can show you the full video. It's fun is not the word for it. I think you'll see why I think sometimes an isosurface is deceiving, let's say. So hopefully this YouTube video works. Probably won't do the full thing, but. Volume rendering. Isosurface. Isosurface. With some transparency. So the thing that we're looking for, how do you interpret these data? All of these biological functions are happening, but do they actually look like these structures? And it almost looks like they're intelligent when they're doing certain things. So like that. It gives you a sense of how things are being structured, how chemical reactions are forming, and things like that, where it actually is that's actually the biological process going on. The isosurface gives you distinct shapes, but I'm not sure how distinct the shapes actually are within the cell biology. But this is actually what your cells are doing on a regular basis. Walking. Seeing back what via chemical reactions, which I find fascinating. But I find the isosurface makes it look like it's very discrete when it's actually not quite as discrete as it might look, like that. I think that's a volume rendering. So, in case anyone's wondering what the heck all of that stuff is, that is what the internal mechanisms for RNA messaging and chemical reactions that are going on in every one of your cells at any given time. So when you're producing RNA or ribonucleic acid, right? So when you're producing RNA for messaging for communication within your cell, that's the kind of stuff that's going on. How you're transporting, essential nutrients into your cell, or how you're exporting waste products out of your cell. All of this stuff is due via chemical reactions, and they're trying to simulate that, or they're simulating it with these visualizations. But it does look like little people working around versus a chemical reaction, which is a lot messier than it actually that would look. And so I'm all sort of on the fence on this, but it tells the story of how these things are actually working, how the chemical reactions happen. It also allows you to visualize the data itself or what we're trying to get across. So, which is part of what I was going to get to next. So if you want Janet Iwaza, I always forget how to pronounce her last name, how animations can help scientists test a hypothesis. I question some parts of her TED Talk, but it's a very interesting TED Talk in terms of providing people with a language, with a way of visualizing and seeing what the data is showing them, giving them the ability to simulate certain things, to test hypothesis with a visualization and a simulation, gives you more bang for your buck. It allows you to test a hypothesis. It allows you to see what your hypothesis would presumably look like. When DNA was discovered, when they realized it was a double helix, I think they just went out for a drink, but it was like, holy crap, we discovered something brand new. It's Watson and Crick's, right? We discovered something brand new, but they couldn't visualize it at the time. They didn't have that technology that this thing forms a double helix. Simulation would allow people to actually see that in action versus just having to look at enough of the data and come to the conclusion the best explanation is a double helix. You can actually test or demonstrate how how biological processes work, how a star goes nova, and what you would expect to see, and what the repercussions would be. That simulation is critical to the scientific process. That's why we look at this the way we do. Okay, our big take-home lesson, I want to give you guys are spatial visualizations are, they're for position in space. What? But occlusion and the sheer amount of data becomes a problem. As a result, we have a whole bunch of little techniques along the way. We have spatial mappings, we have vectors and tensor glyphs, which allow us to see like fluid flow lines. We can also do particles, we can do lines, we can do 2D slices as well of our data. We have volume rendering and isosurfaces to actually show the outside shape, how things are formed and shaped. Not showing magnitude, not showing some other attribute, but showing the actual shape of the thing you're looking at. I don't use volume rendering not so, as much. It's very interesting as an approach. It's just hard to actually read things off of it. But notice what we have here. If I didn't have, this is fluid flow from a river into a dam off the other side. And where I get turbulence, where I have clean fluid flow, where I'm going to be killing fish swimming upstream, essentially. Now, if I have that, so this is the velocity of the water itself, and so this, with the amount of turbulence, it's actually really high turbulence right here and here. That's the kind of thing I need to look into. By allowing me to see how the fluid is, like air is flowing over the airplane, where I have a lot of drag, it tells me where I need to refine my designs. It tells me if I designed it correctly, if I give enough lift on the airplane, if I have abnormal turbulence in here. It is the language that engineers are using to discover the next thing. And this is just, we're producing tools that allow people to do that. So with that, that's not the end of the lecture. I just want to skip over to a completely different topic because I knew this was short. So bear with me for a second. I'm going to cover this, but we're going to go quickly. So, like we're doing, I got 10 minutes, I got 20 minutes on this thing. Dimensionality reduction. It comes up in weird, wonderful ways. And I like just whetting people's appetite for it. We won't go deep diving into it. If we don't do part of it today, that's fine. On Thursday, we're going to talk about how to give a presentation so that the presentations the following week hopefully will not be dumpster fires. Right? Hopefully they'll be better than my presentations. But I've seen enough crappy presentations. I like making sure I go over how to give a presentation. So that's not saying that my presentations are perfect. It's just saying things to be aware of while you're designing your presentation. The presentations last term for 2100, because they were recorded, the presentations were phenomenal. They were really, really impressive, especially for some of the groups, because they could practice, they could do retakes, that sort of thing. We're not expecting to do a live presentation, but it does require practice on how to do the narrative and what you're going to be talking about. That's for Thursday's class. What I want to get to is dimensionality reduction. And you're probably wondering, what the heck is that all about? Well, why do I need to reduce the number of dimensions that I have? This is, okay. So between 1922 and 2011, this is I think the Music Genome Project. This is looking at the number of labels, the record labels that are producing music. Here is the average time of the music. We can look at the amount of bass that the music has. We can look at the tempo of the music. We can look at the beats per minute of the music. We can look at what instruments are being used in the music. In fact, that is the whole point of the Music Genome Project, is breaking down all popular music into component parts. As you might imagine, that is a very, very, very complex data set. Each song that they have in this Music Genome Project has, I can't remember the number of dimensions. I thought it was some ridiculous number of dimensions. Let's keep it simple. Let's say it has 22 different dimensions or 50 different dimensions. That's being fairly conservative. When you're talking about a song, then name all the different ways you can describe that song. You can describe it in terms of the title of the song. You can describe it in terms of who sang the song. Different musicians sing different songs, of course. You can talk about it in terms of parts of the melody. You can talk about what the instrumentation is like. You can talk about the length of the song. You can talk about the what record label produced the song. You could talk about the year of the song. You could talk about all sorts of different dimensions. In fact, that is the challenge with a lot of music. We try and categorize our music. Anyone that I know, this is, I used to give this example, but it doesn't work anymore. For anyone that has a CD collection, yes, CDs are these little spinny discs that you'd put into a CD player and you would play them. I know, crazy. My boys do not know they know what a CD is, but barely. But I have a big CD collection. So my wife has a mediocre CD collection, let's say. People like hardcore record collectors are even more extreme than this. They will spend, if you watch the movie High Fidelity, it's a great movie. They will spend, you will spend your afternoon organizing your CD collection or your record collection. Anyone that collects anything, you have that same sort of thing. If you collect baseball cards, if you collect comic books, you collect anything, you do the same thing. You spend a large amount of time organizing it. Now the question is, how did you organize it? If I have a music collection, I could organize it based on genre. I can organize it based off of things that are similar. I can organize it based off of the just alphabetical, blindly alphabetical. How does a record cut? Back in the day, a record store, a music store, yeah, those things had to organize it based off of genre, and they'd organize it by genre, and then they organize it alphabetically, typically. But then you'd have things like, what if uh, it's somebody that is featuring another musician, right? How does it get organized? Is it a one-time thing? So a relatively old album now, but just because he died somewhat recently, MF Doom, if you know who MF Doom is, he's a rapper from, where's he from originally? Anyways, this great musician, did a lot of albums by himself. Then he did one collaborative album with Danger Mouse. So the name of the album is Danger. The group, quote unquote, is Danger Doom because it's Danger Mouse and MF Doom. What is it listed under? Do you put it under MF Doom? Do you put it under Danger Mouse? Do you put it in its own album, its own place? What do you do with all these different categorizations? That's what we're talking about, is not just how to categorize, but we have high dimensional music spaces with a lot of weird edge cases, and we don't know how we can compare and contrast things. What I would like to do is, if I have a whole lot of music, I like to be able to organize and find the next music for me to discover. I'm an old man. I have 2 kids. My taste in music stops. I'm dead serious. My taste in music, I used to have a pretty good taste in music, and it just stops dead in 2010. The moment my first son gets born, my appreciation for music just goes out the window. I have no time to listen to all this new music that I wanted to listen to, and I just stop. It's like a time capsule. Yeah, good music, good music, good music. Bang, 2010, and now I'm just buying the albums of the bands I was listening to before that happened. But I'm not discovering a lot of new stuff. A couple new things, but not much. If I want to discover new things, how do I discover new things? That's dimensionality reduction. How do I let a visualization represent really complex stuff to let me find new music? If I like, let's go with me, Arcade Fire, The National, St. Vincent, MF Doom, Nico Case, name a couple other musicians, new pornographers, take all of those. They have nothing, very little in common. They have some things in common, but not that much. Now, what's the music that's the next thing I should be listening to? I don't know. You probably don't know, right? We're looking for things, and not just, here, try this, but let me explore the space. Amazon will say, here, try this, and it'll give me garbage. It will be things like, hey, why don't you listen to One Direction? One Direction has nothing to do with any of the bands I was pointing out. At least I hope not, right? They're radically different. Listen to, Christina Aguilera. No, I don't want to. Name some other new pop star, right? I don't want to listen to that. I want to listen to something else. But how I find that new music is different. So I have very high dimensional space. It could be the complete works of William Shakespeare. Find patterns in it. It's text now. It's high dimensional space. There's a lot of differences in all these different parts, and what chunk of text I interpret at a time differs. How do I translate it into a space that I can actually explore? So the Music Network from 2012 looks at this sort of thing. It tries to lay it out in a two-dimensional space as best it can. The question is, how do you do it? And the real answer here is, we can do a number of things. Number one thing we can do is just a projection. So we have this high dimensional space. This is just a metaphor for it. We have this high dimensional space, and all we do is shine a light on one end, project it onto a two-dimensional space. So we choose the best place to put the piece of paper, the best place to put the flashlight in this crazy dimensional space and project it onto two-dimensional space. Or we can try and keep things together as best we can and squish it down. We can't actually represent really crazy dimensional space in 2D or in 3D or some other smaller dimensional space. The challenge is, can we keep as much as possible? Can we keep the essence of those connections so that I can find new music or I can find commonalities in Shakespeare? Or here is a bunch of text from emails. Here is some function that we can analyze the text itself. Can we determine if it's spam or not? Can we explore how much it's like spam or how it's not? Not just is it spam or not, but can we make a visualization to help people understand how much it's like spam? So machine learning will give you this. Letting a human understand how the machine learning algorithm works, that's open-ended. So here are different things. We might have to stop after a couple of these. Our different approaches are, we can try and find principal dimensions, things that are critically important. You can let a machine learning algorithm or some other algorithm find what is important, like the number of beats per minute determines the kind of music that you like, maybe, right? That is a dimension you can find. If you analyze the data, the things in common is you like a large number of beats per minute. Therefore, the music we're going to suggest is something with a large number of beats per minute. You figure out the primary dimensions that categories or differentiate things. So then you align everything based on those dimensions, and then you just show that. Or because it's a high dimensional space, you can just squish it. This is how I pack. So my wife packs like this. It's very organized. She lines everything up. And I pack like this down at the bottom, which is just squish it together. It's going to eventually work, right? Especially if you just have underwear and clothes and stuff, just squish it down. You'll fill in the spaces. This is finding the lowest energy form. Just squish it down and eventually it'll work. So the difference here is, and we have one more thing we can look at. We can look at locally preserving, as in the things that are similar to each other. I want to keep them similar to, like, the neighborhood where they're similar to each other. I want to keep them similar, or I want globally optimal. That's a different thing. So we have things like principal component analysis, PCA, that is finding the dimensions that are important for all of these, all the different types of, let's say, music. What is the dimension that's really important? Organize things based on that. Isomaps say keep things that are similar to each other, keep them together. So Hurt by Johnny Cash and Hurt by Nine Inch Nails, same song. They probably should be put near each other, despite the fact they sound, well, other than the tune's the same, but they're very, very different songs, but they're highly, highly related. They're in different genres of music, though, even. One's country, one is alternative, one's industrial, to be more precise, right? They're very different, but they're the same song. I want them to stay together, despite the fact globally they should be on radically different areas on this music space. So our different approaches. We can reduce the number of dimensions, just linearly reduce it. We just choose the dimensions that are important, keep those, throw everything else out. We can non-linearly just squish everything down. This is multi-dimensional scaling. And then we also can also detect things that are parts of our data and choose to keep those the shape of our data. So instead of saying, let's find a dimension, we say, what we need to keep in mind is certain interesting shapes in our data, and we have to keep that no matter what. Or we just keep all of our data, which is what we were looking at before, which is if I have a scatter plot matrix, it's just that grid of different scatter plots. We show all the dimensions all at once, all in one big grid. I want to see if I can give a good, so this is manifold detection, right? How do I represent this shape? This has a clear shape. It's a spiral shape here. When I reduce it down into two-dimensional space, I need to convey that general shape. And I'm choosing the dimensions. I'm choosing how to map my data into two-dimensional space using that. Let me see here. I want to see if I can find something really good here. I don't think I've been being overly crazy. So let me just stop at this point because I think most of you are like, what is he talking about? What I wanted to point out is there are things far bigger than what we've talked about in this class. There are things where we have a lot of data all at once, a lot of people, a lot of data, and we're trying to represent it in two-dimensional space. And that's where we get into cases of how we try and translate something very complex into an easier lower dimensional space. And that can take a lot of computational overhead. It requires a lot of math, and it's not as simple as saying, I'm just going to choose this, I'm going to just choose this willy-nilly. Sometimes you want to actually figure out how to represent really complex things in a methodical, analytical way using the math. And that is a whole other field that we can look at as well when you're talking about similarity between two different things. It's not just based off of dimensions you can see. Sometimes there's something else underlying it. And this gets into this rabbit hole of the statistics and how they relate to visualizations. Okay. When we come back next time around, we are going to be doing the how to give a presentation, and then we're going to be doing the usability testing on Thursday during the lab period of time. In the meantime, I'm going to have a quick snack, and then I'm going to be back around for, we'll be doing office hours. I won't necessarily leave the Zoom open, but just let me know if you want a shot. You can throw it, ask me on Discord or anything like that. And I can help you out with your projects, right? I'm also going to try and post your sprint grades as quickly as I can. All right, thank you everyone, and I'll talk to you on Thursday.